Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, for just a second, that you are standing outside on, like a perfectly clear, crisp night. You're just looking up at the vast, sprawling expanse of the night sky, right?
Right, getting that full cosmic perspective.
Exactly. And the stars, they appear completely fixed. The planets are slowly, silently tracing these ancient, mathematically predictable paths.
It's basically orbital mechanics doing its thing.
Yeah, and everything just feels ordered.
Yeah.
Like the universe, from our terrestrial vantage point anyway, it looks like a flawless, frictionless clock.
A very large, very cold clock.
Right. Now, I want you to imagine locking your eyes onto a specific celestial object that's just hurtling through the darkness.
Okay, I'm picturing it.
It has mass. It has momentum. It has been traveling on this massive elliptical track for centuries, literally doing exactly what the laws of thermodynamics and gravity demand that it do.
Because that's how physics works. You can't argue with inertia.
You can't. But then, right as you're watching it, the impossible happens. This ancient object completely slams on the brakes.
Which is wild.
The rotation just grinds to a dead stop. And then, completely defying everything we intuitively understand about momentum, inertia, and, the absolute vacuum of space, it starts violently spinning in the exact opposite direction.
Yeah, it fundamentally breaks the brain's intuitive physics engine.
Totally.
Because when an object with that much mass and that much established inertia suddenly reverses course in a frictionless environment, it feels like a glitch in reality.
It really does. Like someone just hit reverse on a remote control.
Exactly. It goes against our fundamental understanding of how large celestial bodies are supposed to behave. I mean, you expect a planet or a moon to gradually slow down over, say, billions of years due to tidal forces.
Right, billions of years, not over a weekend.
Exactly. A sudden, violent mechanical reversal on a human timescale. That requires a localized application of force so massive and so chaotic that it almost seems engineered.
Which is why this is arguably one of the most fascinating astronomical anomalies on record.
Right.
We aren't just talking about like a theoretical model or a broken piece of video game physics here.
No, this is heavily documented.
It's a very real event surrounding a specific object known to astronomers as Comet 41P Tuttle Giacobini Kresák.
Quite the mouthful.
Yeah, we are definitely going to call it 41P to save oxygen.
Good call.
Okay, let's unpack this because our mission today is to entirely break down this unprecedented event. We're talking about the first ever observed instance of a comet throwing itself into a reverse spin.
And what makes this story truly brilliant isn't just the violent physics of the reversal itself.
Oh, right. It's how we found out about it.
Exactly, because we didn't catch this happening live. The evidence of this impossible cosmic spin-out was just sitting quietly in a digital database.
Like a ghost in the machine.
Yeah, completely unnoticed until someone decided to sift through the archives and actually do the math. The archival nature of the discovery is perhaps the most compelling part of the narrative here.
Because it completely recontextualizes how we view modern astronomy. We aren't just looking up anymore.
All right, we're looking back through the hard drives.
So we're going to explore the chaotic physics of the inner solar system, the rapid, almost violent life and death cycles of short-period comets, and basically the hidden treasures buried inside decades of data.
Because to really grasp the magnitude of what happened to 41P, you have to understand the specific structural vulnerabilities of the comet itself.
Yeah, it's not just a generic space rock.
No, it is a remarkably fragile piece of primordial architecture.
So let's start with that architecture.
Yeah.
Because if a solid object stops spinning in a vacuum, the kinetic energy doesn't just magically disappear, right?
Right. Physics demands an equal and opposite reaction.
Exactly. So before we can identify where that massive counterforce came from, we need to understand exactly what kind of object is receiving the blow. Let's meet our protagonist.
Let's do it.
Where does a rock like 41P actually come from? Like, initially?
Well, to find the true origin of 41P, you have to look outward, like far past the orbits of Neptune and Uranus.
Way out there.
Yeah, to the absolute freezing dark edges of our solar neighborhood. We're talking about the Kuiper Belt.
Okay, the Kuiper Belt.
It's this massive, incredibly sparse ring of primordial frozen debris. The objects out there are basically the leftover building blocks from the very formation of the solar system.
So roughly 4.6 billion years ago.
Exactly. They are essentially preserved in a deep freeze, totally untouched by solar radiation, just drifting in a state of near-perfect cryogenic suspension.
So it basically spends billions of years just floating in the dark, like a dormant time capsule of ice and rock.
Yep, just waiting.
So how does something locked in the deep freeze of the outer solar system end up zooming past Earth? Like, how does it get hot enough to fundamentally alter its own mechanics?
Oh, well, it encounters the ultimate gravitational bully of our solar system.
Jupiter.
It is so staggeringly massive that its immense gravity, well, it dictates the architecture of basically everything around it.
It's kind of a cosmic vacuum cleaner, right?
A vacuum cleaner and a gravitational slingshot. Because at some point in 41P's ancient history, its slow, lazy orbit drifted just a fraction too close to Jupiter's sphere of influence. And the giant planet's gravity caught it, warped its trajectory, and fundamentally flung it inward toward the sun.
It's basically orbital resonance acting as an eviction notice.
A permanent one, yeah. That interaction completely rewrote the comet's destiny. It left 41P locked into a brand new, highly elliptical path.
Right.
It became what astronomers classify as a Jupiter family comet. So its orbit now brings it swinging through the inner solar system, relatively close to the sun and Earth, every 5.4 years.
Okay, 5.4 years.
And based on dynamic orbital modeling, researchers believe it has actually been trapped in this exact 5.4-year loop for approximately 1,500 years.
That is wild. A millennium and a half of doing the exact same lap.
Round and round.
5.4 years out toward the cold of Jupiter, then whipping back around into the searing heat of the sun. But when I picture a comet surviving that kind of extreme thermal cycling for 1,500 years, I picture something the size of a city.
Yeah, that's the standard mental image.
Right. Like I picture a massive apocalyptic mountain of ice, like Hale-Bopp or Halley's Comet.
And that assumption is exactly why 41P is such a profound mechanical anomaly.
Okay.
Because the nucleus of Comet 41P, and I mean the actual solid core of rock, dust, and ice, beneath the glowing coma you see in photographs, it is almost unimaginably small.
How small are we talking?
It measures only about 1 kilometer across.
1 kilometer. Okay, just to give you a concrete visual anchor for that scale. Picture the Eiffel Tower in Paris.
Okay.
Now imagine stacking 3 Eiffel Towers end to end. That total height is roughly the diameter of this entire comet.
It's a tiny.
On a human scale, sure, looking up at 3 stacked Eiffel Towers floating in the sky would be massive.
Terrifying, really.
Right. But in the arena of orbital mechanics,
Yeah.
in a space populated by moons and gas giants,
Yeah.
that is essentially a microscopic speck of dust.
It is remarkably diminutive. And that lack of physical volume translates directly to a severe lack of mass.
Makes sense.
Because 41P is so small, its own self-gravity is incredibly weak. In fact, the escape velocity on a 1-kilometer comet is so low that if you were standing on its surface, you could simply jump, and your leg muscles would provide enough kinetic energy to break the comet's gravitational hold entirely.
Wait, really? You just jump into orbit?
You would just float away into space. You'd never come back down.
That is insane. Which means the comet itself barely has the internal cohesive strength to hold its own material together, let alone resist external forces.
Exactly. It is highly susceptible to torque.
Right, torque.
Yeah, torque is simply the measure of force that can cause an object to rotate about an axis. When you have an object with substantial mass, say a 50-kilometer wide comet, it possesses a massive moment of inertia.
It's heavy.
Right. It takes a staggering amount of energy to alter its rotation. It can essentially shrug off environmental forces. 41P does not have that luxury. It is a lightweight.
Think of it like a quadcopter drone, right?
Oh, that's a good comparison.
Yeah, like if you have a massive military-grade helicopter,
Yeah.
a sudden gust of wind or a minor mechanical hiccup isn't going to flip it upside down.
Yeah.
Its sheer mass anchors its momentum. But if you have a cheap, lightweight, palm-sized plastic drone, and one of the 4 rotors suddenly fires at 300% capacity while the others remain normal, the drone doesn't just drift sideways.
No, it completely wipes out.
Exactly. The massive asymmetry and thrust against its low mass throws the entire machine into an uncontrollable violent flat spin. In the grand chaotic mechanics of our solar system, Comet 41P is that tiny, unbalanced drone.
The drone analogy captures the mechanical vulnerability perfectly. It is structurally at the mercy of the thermodynamic environment around it.
And that extreme vulnerability is really what sets the stage for the deeply bizarre sequence of events that astronomer David Jewett eventually uncovered.
Yes. The entire timeline of 41P's 2017 approach to the sun basically reads like a forensic reconstruction of a mechanical failure.
So let's trace that 2017 timeline, because it really is a detective story.
It really is.
We are following the breadcrumbs left in the digital archives.
Yeah.
And it starts in March of 2017, when 41P was making its standard 5.4-year swing toward the sun.
Right. In March, the astronomical community had their eyes on it. Astronomers utilized the Discovery Channel telescope, which is a very powerful ground-based optical observatory located at the Lowell Observatory in Arizona.
Very famous telescope.
Oh, yeah. So they took standard photometric observations, basically measuring the light curve of the comet as it tumbled through space.
So a solid baseline measurement.
Exactly. The March data established the comet's starting parameters. They calculated how fast it was spinning as it came in toward perihelion, which is its closest approach to the sun.
And what was it doing?
At that moment, it was behaving like a perfectly standard, albeit very small, Jupiter family comet. Its rotation was normal. Its momentum was steady.
Okay, but the narrative fractures just 2 months later.
Right.
Fast forward to May of 2017. If I'm David Jewett looking at this archival data, what am I seeing in the May files?
You are seeing an inexplicable deceleration. In May, researchers pulled data gathered from space, specifically from NASA's Neil Gehrels Swift Observatory. Now, Swift is primarily designed to hunt for gamma-ray bursts deep in the cosmos.
Oh, really? Not comets.
Right. But its ultraviolet and optical telescopes are occasionally pointed at local targets like comets. And the ultraviolet data from Swift revealed something entirely baffling.
What did it show?
In just an 8-week span, the comet had experienced a massive, dramatic slowdown in its rotational period.
A slowdown in a vacuum implies a massive counterforce. I mean, there's no air resistance to bleed off that momentum, right?
None.
So what kind of deceleration are the Swift numbers actually showing?
The object was suddenly spinning 3 times more slowly than its baseline measurement in March.
3 times?
Yeah, the rotation period had stretched out to a sluggish, agonizing crawl, taking anywhere from 46 to 60 hours to complete a single rotation. It was literally grinding to a halt.
A comet that has been doing the same lap, carrying the exact same momentum for 1,500 years, suddenly loses 2/3 of its rotational velocity in 60 days.
It's unheard of.
That alone is a terrifying display of localized force. It's a massive physics anomaly. But that isn't the climax of the archive, is it?
No, the actual shock comes at the end of the year.
Okay, let's get into that.
We're moved to December 2017. This is the crucial file that Jewett eventually cracked open. The observations this time came from the Hubble Space Telescope.
Oh, the big guns.
The biggest. Hubble's optics are pristine. It operates entirely above the distortion of Earth's atmosphere, providing incredibly high-resolution imaging.
Right.
When the December light curves from Hubble were finally analyzed, they showed that the sluggish 60-hour crawl was totally gone.
So the rotation sped back up.
It accelerated wildly. It went from that 60-hour crawl back down to completing a full rotation in just 14 hours.
Wow.
It was whipping around. What's fascinating here is the direction of the rotation had flipped. It was spinning in the completely opposite direction from its March baseline.
A violent, massive mechanical reversal over a span of just 9 months. Think about the energy required to execute that maneuver. It had to continue slowing down after the May observation, eventually coming to an absolute dead mechanical stop in the vacuum of space before being forcefully, continuously pushed to accelerate backward.
It really forces a complete reevaluation of the thermodynamic forces at play on the surface of these small bodies.
I bet.
Because to fundamentally alter the angular momentum of a 1-kilometer-wide solid object, you need a continuous, targeted, and immense application of force. You literally need an engine.
Which brings us to the mechanics of the vacuum itself. We have the forensic timeline, right? Normal spin, sudden deceleration, dead stop, violent reverse acceleration.
The whole sequence.
We know the mass is low, but where is the engine? Like, what massive force in the solar system could possibly act as a localized thruster system capable of throwing 3 Eiffel Towers into reverse?
The engine is fueled by a very specific phase transition called sublimation.
Okay, sublimation. Let's break that down.
When we interact with ice on Earth, we are dealing with atmospheric pressure. If you take an ice cube out of your freezer, the ambient heat causes the solid H2O to melt into liquid water.
Right, it melts.
And if you apply enough heat, that liquid water eventually boils and evaporates into a gas. That is the standard thermodynamic progression: solid, liquid, gas.
But a comet operates in the deep vacuum of space. The atmospheric pressure is essentially zero.
Exactly. And without atmospheric pressure, the liquid state of water simply cannot exist.
Really?
Yeah, the physics won't allow it. So as Comet 41P approaches the sun, it is subjected to incredibly intense, unshielded solar radiation.
It's getting baked.
Baked. The surface of the comet heats up rapidly. The frozen volatiles, things like water ice, carbon monoxide, carbon dioxide, they react to this extreme thermal shock by instantly flashing from a solid state directly into a gaseous state.
Wow.
They bypass the liquid phase entirely.
So it's flash boiling from a frozen rock straight into a violent cloud of vapor.
Yes. And that vapor doesn't just passively float away like a morning mist. Because it expands incredibly rapidly upon transitioning to a gas, it violently, forcefully ejects outward into the vacuum.
Like an explosion.
Very much so. This violent expulsion creates localized outgassing jets right on the surface of the comet's nucleus.
This is where David Jewett's analysis of the Hubble data becomes so brilliant. Because he looked at these outgassing jets and just applied absolute foundational Newtonian physics to them.
Newton's third law.
Right. For every action, there is an equal and opposite reaction. As the sublimating gas violently fires outward into space, the physical force of that ejection pushes back against the solid surface of the comet.
It is the exact same mechanical principle that propels a SpaceX rocket off a launch pad.
That's a great way to picture it.
The rocket forces combustion gases downward, and the equal opposite reaction pushes the massive physical structure of the rocket upward. On 41P, the sublimating ice is acting identically to chemical propellant. The comet has essentially grown a series of organic, entirely uncontrollable rocket thrusters all over its surface.
But wait, if you have thrusters covering the entire surface of a sphere, pushing equally in all directions, the forces would just cancel each other out, right?
You would think so, yes.
The comet would just sit inside a glowing ball of its own gas.
Yeah.
I mean, it might get pushed slightly outward away from the sun by solar wind, but its spin wouldn't violently throw itself into reverse.
Right, but you are assuming a comet is a perfect, smooth sphere,
Right.
and they almost never are. Because 41P is so small, it lacks the necessary mass to achieve hydrostatic equilibrium.
Which is what?
That's the gravitational force that pulls planets and large moons into perfect round shapes. 41P is lumpy, irregular, scarred, and completely asymmetrical. It looks more like a battered potato than a billiard ball.
Ah, okay. And because the shape is asymmetrical, the distribution of the ice is asymmetrical.
Exactly. The active areas, the exposed patches of volatile ice that create the strongest jets, were unevenly distributed across its irregular surface.
So it's not a uniform push.
Not at all. So when the sun hit those patches, the thrusters didn't fire symmetrically. They fired off-center. They fired at odd angles. And the dominant force of those asymmetrical jets happened to push directly against the comet's original rotational motion.
Here's where it gets really interesting, because Jewett used a brilliant analogy in his analysis to make sense of this torque. He compared the comet to a playground merry-go-round.
Such a helpful visual.
It really is. Imagine a heavy metal merry-go-round spinning steadily to the left. If you run up to it and start aggressively pushing against the metal bars, forcing them to the right, the merry-go-round doesn't just instantly snap into reverse.
No, it has momentum.
Right. The first thing that happens is it begins to aggressively decelerate. Your pushing is fighting against the established angular momentum.
And that deceleration is exactly what the Swift Observatory captured in May of 2017.
The slowdown.
Yes. The sun's intense heat had activated the comet's asymmetrical thrusters, and the physical force of those gas ejections started pushing continuously against the comet's natural forward spin. The spin was bleeding off energy, slowing to that sluggish 60-hour crawl.
But the sun doesn't just turn off. The thermal shock continues as the comet gets closer to perihelion. The sublimation doesn't stop.
It actually accelerates.
Right. So, back to the playground. You don't stop pushing the merry-go-round to the right. You keep applying force. Eventually, the forward momentum is entirely depleted. The merry-go-round grinds to a dead stop.
Feels zero momentum.
And then, because you are still leaning your entire weight into it, pushing right, it begins to accelerate into a rightward spin.
Exactly. The continuous, wildly uneven outgassing eventually overpowered the entirety of the comet's original angular momentum.
It's mind-boggling.
It really is. It applied enough counter-torque to stop a 1-kilometer rock dead in its tracks and then functioned as a retrograde engine, spinning it up until it was whipping around every 14 hours by December. The physics are totally sound, but witnessing the sheer scale of thermodynamic energy required to execute that maneuver on a solid body is staggering.
It's an incredible display of mechanics. But as Jewett dug deeper into the data, this violent spin reversal started to look less like a quirky physics trick and more like a medical symptom.
Sadly, yes.
It points to something much darker regarding the structural integrity and the overall lifespan of 41P. The comet is essentially experiencing a violent terminal crisis.
Yes, we have to zoom out from the 2017 event and look at the comet's historical health. Because to contextualize the violence of the spin reversal, you have to look at the volume of gas the comet was actually producing.
Right.
And the archives provide a chilling point of comparison.
So let's pull up the data from its previous close passes. 41P loops the sun every 5.4 years. What did it look like in the past?
The most vital comparison point is its perihelion passage in the year 2001.
Sorry, 2001.
During that approach, 16 years prior to the spin reversal, astronomers recorded that 41P was exceptionally active for a comet of its diminutive size. Oh yeah, it was venting brilliantly. The volatile ice was reacting violently to the sun, producing a massive dense coma of gas and dust. It was a robust, highly healthy textbook comet.
But when we fast forward back to the 2017 passage, the exact same orbital path, the exact same proximity to the sun, the health metrics just collapse.
You fall off a cliff.
The overall gas production of 41P didn't just dip. It plummeted by roughly an order of magnitude. It dropped by a factor of 10.
Yeah.
It was producing only 10% of the gas it had produced just 16 years prior.
Yeah.
90% of its activity simply vanished.
That kind of severe, almost instantaneous drop in outgassing is alarming. Astronomers generally accept two primary hypotheses for why a short-period comet would undergo such a massive and rapid loss of activity.
Because let's unpack the first hypothesis. What's the main idea?
The first is simple volatile depletion.
Okay.
The comet is fundamentally running out of fuel. You have to remember, 41P has been running this exact inner solar system loop for 1,500 years.
That's a lot of trips around the sun.
It is. Every 5.4 years, the sun burns off a layer of its near-surface ice. After a millennium and a half, the tank is simply hitting empty.
Wow.
The accessible ice that is actually capable of sublimating has been exhausted, leaving behind mostly inert rock and deep core ice that the sun's heat just can't easily reach.
So it's drying out. It's transitioning from a vibrant comet into just a dead, inert asteroid.
Exactly.
So if the tank isn't simply empty, what's the alternative? Is the fuel somehow trapped?
You're hitting on the second hypothesis, mantling.
Mantling.
Yes. Mantling suggests that the volatile ice is still present beneath the surface, but it is being aggressively smothered.
Smothered how?
Well, when a comet sublimates, the gas expanding into space carries dirt, dust, and heavier silicate particles with it. But because 41P has such weak gravity, not all of that debris reaches escape velocity.
So it doesn't all blow away.
Right. A lot of the heavier dust eventually falls back down onto the nucleus. Over hundreds of orbits, this fallback creates a thick, highly insulating crust of dust and dirt over the active ice patches.
Wait, hold on. Let me push back on the mantling theory for a second.
Sure.
If the comet is building up this thick, insulating crust of dust, wouldn't that actually act as a heat shield? Like if the crust prevents the sun's thermal radiation from reaching the ice, the sublimation stops.
True.
And if the sublimation stops, the rogue outgassing thrusters shut down. So doesn't the dust crust actually save the comet from continuing to spin out of control? It seems like mantling would stabilize the rotation, not make it worse.
It's a brilliant deduction, and in a perfectly uniform system, that might be true.
Sure.
A perfectly even mantle would shut down the comet entirely, turning it into a dormant rock.
But
again, 41P is heavily asymmetrical and chaotic. The mantle doesn't build up evenly. You get thick crusts in some areas and exposed highly active vents in others.
I see.
This extreme variance in surface insulation actually exacerbates the asymmetrical thruster problem. You have concentrated, hyperpressurized jets firing from the few remaining weak points in the crust.
So instead of a dozen small thrusters pushing evenly, you have one or two massive concentrated geysers fighting against the entire mass of the comet.
Exactly.
It makes the torque even more violent.
Furthermore, even beneath the mantle, the heat slowly permeates. The ice beneath the crust still sublimates, but the gas is trapped.
Oh, a pressure cooker.
Yes, it creates localized high-pressure subsurface pockets that eventually explode through the crust, creating sudden, violent bursts of momentum. Whether it is depleting its fuel or choking on its own debris, the timeline is what truly shocks the astronomical community.
Right, the 16-year gap.
Yes. The structural evolution of comets, the gradual building of a thick mantle, or the complete exhaustion of volatile reserves, these are processes that standard models dictate should take centuries or millennia.
Right, space-time is deep time.
We assume these changes happen on deep cosmic timescales. But with 41P, the data proves it dropped 90% of its activity in just 16 years. We are watching cosmic evolution, the actual aging and dying of a celestial body unfolding on a human timescale.
Which naturally forces us to look at the math of its future. We have a rapidly deteriorating comet. We have a wildly fluctuating asymmetrical rotational spin. We have a structurally compromised, weak body of ice and rock.
A recipe for disaster.
When David Jewett ran the predictive modeling on these specific torques and mass loss rates, what does the physics say happens next? How does the story of 41P end?
The physics point toward a mathematically inevitable and highly violent conclusion. The continuous radical changes in angular momentum are subjecting the comet to extreme mechanical stress.
I can imagine.
And the ultimate threat here isn't the sun's heat melting it away. The threat is centrifugal force.
Okay, let's make sure the mechanics of centrifugal force are perfectly clear for everyone. If you take a wet tennis ball, soak it in a bucket of water, and then spin it incredibly fast, the water violently flies outward in all directions.
Exactly.
The spinning motion creates an outward push, pulling mass away from the center of rotation. If you spin something fast enough, the outward centrifugal force becomes stronger than the internal bonds holding the object together.
And we return to the core vulnerability of 41P, its diminutive size. Because it is only 1 kilometer wide, its self-gravity is incredibly weak.
Right, you could jump right off it.
Furthermore, comets are not solid blocks of granite. They are highly porous, structurally fragile agglomerations of ice, dust, and loose rock. They are essentially giant, loosely packed, dirty snowballs.
That's a great way to put it. Dirty snowballs.
Their internal tensile strength is remarkably low.
So it's barely holding itself together under normal circumstances.
So as these rogue outgassing jets continue to misfire, if they push the comet's rotational velocity just slightly past a critical threshold, the outward centrifugal forces will completely overpower the comet's weak gravity and its fragile internal cohesion.
Oh, man.
The force attempting to fling the material outward into space will become greater than the gravity pulling it inward.
It hits the rotational equivalent of the Roche limit. The internal physics just give up. And what does that look like? Does it just crack in half?
It looks like catastrophic disintegration. The nucleus will literally tear itself apart from the inside out.
Unbelievable.
It will shatter into a massive debris field of expanding ice, dust, and boulders, completely dissolving its physical form and spreading its remains across its 5.4-year orbital trek. David Jewett looked at the torque calculations and was completely unambiguous about the prognosis.
What did he say?
He stated, "I expect this nucleus will very quickly self-destruct."
Wow. Very quickly self-destruct. It's chilling to hear an astrophysicist use that kind of definitive, violent language regarding a celestial body.
It's rare.
It paints a profoundly different picture of the solar system than the one we usually imagine. You have this object that survived the chaotic formation of the solar system 4.6 billion years ago. It survived being violently ejected by Jupiter. It successfully navigated the thermal shock of the sun for 1,500 years. And now, suddenly, it is being ripped apart by its own internal gases, literally spinning itself to death because it can't handle the physics of its own sublimation.
It highlights how utterly fragile these small bodies actually are. They aren't permanent fixtures in the sky. They're temporary, delicate structures entirely at the mercy of the thermodynamic environment.
It is a stark reminder of the dynamic violence of orbital mechanics. But, you know, the entire narrative of 41P's impending destruction is underscored by the methodology of the discovery itself.
Absolutely.
We wouldn't know any of this. We wouldn't understand the violent torque of asymmetrical jets or the incredibly rapid 16-year aging process if it weren't for the philosophy of modern astronomical data archiving.
It's true.
This is the part of the story that I find most inspiring. The unsung hero here isn't a new multi-billion-dollar piece of hardware launched in orbit yesterday.
No, not at all.
The hero is the digital filing cabinet. Right. The hero is the patient, meticulous mining of old, ignored data.
Consider the timeline of discovery again. The baseline observation was March 2017. The swift slowdown was May 2017.
Right.
And the shocking, violent spin reversal was captured by the Hubble Space Telescope in December 2017. But the incredible truth is that when Hubble captured that light curve in December of 2017, no one on Earth realized what they had just photographed.
That blows my mind. The telescope recorded the impossible physics, downloaded the telemetry to servers on Earth, and it was just quietly filed away.
Yep.
No alarm bells went off. No one was watching the live feed shouting, "Eureka!"
It simply became another data point in an impossibly vast ocean of information. To understand how a discovery this massive gets buried, you have to look at the sheer, overwhelming output of modern observatories.
It's a lot of data.
The Hubble Space Telescope has been gazing into the deep universe, collecting high-resolution imaging and complex spectroscopic data for over 3 decades. It is an absolute fire hose of cosmic telemetry.
It's capturing infinitely more data than the global astronomical community can possibly analyze in real time.
Precisely. And because of that immense volume, NASA and the Space Telescope Science Institute established the Mikulski Archive for Space Telescopes, commonly known as MAST.
MAST, okay.
This is a massive centralized repository that holds the raw and calibrated data not just from Hubble, but from over a dozen different space-based and ground-based astronomical missions. Every photon captured, every light curve measured is uploaded into this archive and made freely available to researchers.
It is the ultimate open source library of the cosmos. And it was inside this specific digital library that David Jewett was simply browsing years after the fact.
He was just looking.
He wasn't commandeering telescope time. He was sifting through the MAST records, pulled up the files on 41P from late 2017, and realized that the specific Hubble light curves from December had never been fully modeled.
No one had done the complex mathematical work to extract the rotational period from those specific pixels. Jewett applied the math to the archival data, and the ghost emerged from the machine.
Incredible.
The spin reversal revealed itself on a computer monitor years after the physical event had already occurred in the vacuum of space.
This completely upends the romanticized Hollywood version of science, doesn't it? Wow. We always picture the lone genius peering through a frosted eyepiece on a mountaintop, gasping as a new comet streaks across the lens.
A very dramatic image, but not very accurate.
Right. The reality of modern astrophysics is often much quieter and in many ways much more profound. It is the realization that the truth of the universe, the evidence of a dying comet spinning violently backward, was sitting on a hard drive the entire time.
Hidden in plain sight.
It was like finding a winning lottery ticket in the pocket of a winter coat you haven't worn in 3 years. The data didn't change. The stars didn't change. The only thing that changed was a human being deciding to ask the right question and having the curiosity to look at the old data in the new way.
The philosophy of open science is rapidly becoming the most powerful tool in astronomy. Space exploration is no longer solely defined by the massive, multi-billion-dollar engineering challenges of launching new mirrors into the void.
Right, the hardware is just step one.
Exactly. It is equally defined by data mining. The archive itself is a universe waiting to be explored. By ensuring that petabytes of raw astronomical data are open, preserved, and accessible, we guarantee that observations can be endlessly revisited to answer questions that scientists in 2017 didn't even know they needed to ask.
It's a phenomenal synthesis of human curiosity and raw computational physics. If we trace the entire narrative arc of Comet 41P, we start with a fragile, microscopic rock Asian. Just 3 Eiffel Towers cross-born billions of years ago in the cryogenic deep freeze of the Kuiper Belt. It gets gravitationally bullied by Jupiter, permanently evicted into a 1,500-year loop of thermal torture. Then, in a span of just 16 years, it rapidly ages, losing 90% of its activity as it either exhausts its fuel or suffocates under its own debris.
A tragic end.
And finally, the sun superheats its remaining asymmetrical ice patches, turning them into rogue rocket thrusters that violently break the comet's momentum and hurl it into an unprecedented, catastrophic reverse spin.
It really sounds like science fiction when you summarize it like that.
It does. Now, plagued by the immense stress of centrifugal force, it is mathematically destined to tear its own fragile body apart, leaving nothing but a ghost trail of dust in its wake. And the entire violent saga was decoded from a forgotten computer file.
It perfectly dismantles the illusion of a static universe. The night sky is not a calm, predictable tapestry. It is a highly volatile, violently shifting thermodynamic engine.
Constant motion.
Celestial bodies are constantly reacting, decaying, and being destroyed by the invisible forces of gravity and radiation.
And our ability to comprehend that beautiful, terrifying chaos relies on our willingness to meticulously preserve and re-examine our own records.
Which leaves us with a rather profound implication to consider. If a single unanalyzed file from 2017 could fundamentally shift our understanding of comet mechanics and reveal a completely unprecedented violent rotational reversal hiding in plain sight, what else is in the archive?
That's a huge question.
What other universe-breaking anomalies, dying stars, or silent cosmic catastrophes are sitting quietly on a server right now, completely undetected, simply waiting for someone curious enough to open the file?
The answers to the universe's greatest mysteries might not require a new telescope. They might just require us to look closer at the light we've already captured.